question, I thought, right?
Yes. If they have any questions, Diganta, I mean, on the example, Diganta would be the best person to ask if they have questions about RNN verification, etc. Should be okay. So let's, first let's see if they have any questions.
Yeah.
We can.
Yeah, so Diganta discussed that like the RNN should follow some standard rules, right, for verifying, as in like it should output sentences with proper grammar, right?
Correct.
So how like I don't really see any way how to verify that. If you could give some insight into that, that would be great. Like some basic high level insight.
Yeah. Well, he discussed three properties. Okay. So you're asking about so how you would encode that it meets some specified grammatical constraints. Correct? That's your question.
Yeah.
Yeah. So how do you think you would? I mean, how would you forget about the encoding part? Okay. How would you, as as a human being, okay, you would determine whether something is grammatically correct or not?
Oh, so I would like to have some set of rules, as in like basically generating grammar, right?
Correct. Yeah. So you would have to, the most general way of doing it is you will have to have a grammar, but for a natural language, the grammar would be pretty hard, isn't it? Okay. It is not going to be as simple as even a context-free grammar or anything, right? So it will be a complex set of set of rules. So that is one way. If you want to, I mean, assuming that you put some restrictions, you can express it as some rules, even if not complete. You could, Diganta is here. So that is one way. You could express them as rules of what is acceptable. By the way, Diganta, I'm just there was a question from, I guess, who? Devjit, is it?
Yes, sir. Yeah.
Yeah. How to specify among the three properties? I mean, the properties that you discussed last time. One of them was a correctness or an expected, property, which says that that the set of sentences that it has to recognize has to be meaningful. Okay. As per some rules. Okay. So the question was, how would you express that formally? Okay. So
like some high level ideas would be fine. Like
so I think so you have to specify some rules, even if those rules are not complete. The rules could say that if those rules are not met, I guess it still would be okay, but certainly you can say that these are not permitted. Okay. So that is one way I can think of. Okay.
So I had this question.
Or you could have, to get, let me finish. Okay. To get a complete grammar for natural language processing is pretty hard. And I think natural language grammars are fairly complicated and, that are used by some of these speech, natural language processing systems. How that itself is fairly complicated. So, okay, so that would be, we'll have to put some constraints on what is certainly not acceptable. That is one that I would, that is one way to approach it. Okay, so that's a good question. If indeed that is a property that we want you to investigate, Diganta, then we'll have to specify how exactly, what is the scope to which we would want them to specify and verify that property.
Yeah, I think that like some simple rules that either should always hold or should never hold.
Never hold. Yeah.
Yeah. So a few list of that depending upon what kind of like if it's English text, something like space after full stop and then capital letters or some things
Correct.
like that we can.
Yeah.
Yeah. So, but like till this point, we have seen verifying things like, oh, if this thing is in this range, then this should also be in this range, right? So,
Yeah.
how to translate to that?
So how do you mean range? What do you mean by range?
So the inputs being in the range of -3 to 3, the output or the hidden layers will be in some specified range.
No, why is that difficult? Why was that?
That is what we have done up till this point, right?
Correct. Yeah. So, what you just now said is not hard to specify, isn't it?
Yeah, it is not hard to specify. So
Correct.
that's the thing. But like, how to specify these problems to like maybe, so does the translation of the property of the grammar turn into such problems is
Yeah,
what I'm
no, but
asking.
that I think there is another layer there, okay, because everything will then be reduced to some kind of probability that it will recognize it as something, as the probability of it recognizing some word or some sequence of words as, if it's a sequence of words as some text. So you will have to then say that the probability that at which it will recognize it as per the allowed rules and as per the rules that you specify has to be something greater than certain things. Okay, so that's how I would do. So the rules that you have will be used in your specification to say what is right and what is wrong, okay? And then your property can be that with certain probability that anything that it recognizes, anything that it recognizes, when it recognizes, the probability that it recognizes correct has to be above a certain number, or the probability at which it'll make an error, that it'll recognize it wrongly, should be below a certain thing. I mean, that's how I had in mind, okay, where you could specify it. So then your encoding will then use that. We'll have these two parts where the probability thing will be the actual value of what you get at those outputs or at those specific nodes. And then there will be another relation, a part which will say exactly what it means to be correct and not correct, which will involve the roots. So you'll have to combine these two things in your specification. Is what I would guess the way that I would do. I mean,
Yeah,
I
guess that answers.
haven't specified all the details. You could have as some black box what it means to say some sequence of words is satisfies certain rules. What it's as another predicate which says, oh, this is wrong. Okay, let's suppose that you separate that specification of that predicate. Okay, given a vocabulary, given certain rules, and so on. Okay. Suppose that is specified separately as a black box. Then your overall property will then have to have a part which will relate these two things, the probability part and the correctness part.
Yeah, I guess that makes sense. Yeah.
Yeah, Viganta, you haven't uploaded yet your code that they could run or experiment with, have you?
No, I will do that.
Yeah, I think we should, when we are, okay, so we are close to this. 15 minutes is a limit that I want to put. Okay, we can always discuss offline and individually. So I think, we'll have to tell them what it is, the actual steps, suggested, proposed steps that they will go through, and specify some interim documents that they'll have to produce to make sure that they are making progress. Okay, milestone documents that we'll have to specify. Okay, right now, immediately, what is it that we want them to do?
I think right now, immediately until I upload the code, nothing much can be done. So I guess I'll have to do
Yeah,
that.
but that's so they will, by running it, they will understand what how the RNN, I mean, that kind of a structure works, no?
Yeah.
On this particular recognition problem. And but when you have what you've trained them, etc., or are on a particular set of with a particular recognition goal, or how have you done it?
Yeah, so the one that I have trained is trained on some Shakespeare text. So that would be some English text with it'll follow all of your standard English grammar and such things. So that can be used.
Yeah. So what you have done is so that the rules are not clear there, because it may. Yeah, the specification. So it is trained as per some data that you have generated. That says what is correct and what is not correct, and you have based it on that, correct?
Right,
yeah. So maybe that should be published as well.
Yeah,
so
sure,
that
sure.
you publish that, then they can make up. If you want them, if you require them to, for that property that he mentioned, if you want to say what it means to be correct, what is not to be correct, okay, you will have to do it separately, no? And you can use that data as a reference point as well. Huh?
Yeah, that's true. Yeah. So so that I'll publish, and then they can.
Yeah. So here, when we do it like this, there's already a gap that I can see, because even the specification is not easy. I don't know how you would specify what is correct, because there will be a gap. Maybe the system, the network might be able to do better than what it is specified. No?
Yeah. So
some cases.
I mean, in some cases, yes, but if we can verify that it will always follow some basic grammar, then that's a good thing to verify, right?
Yeah, that's why I think it's better that more valuable will be what it should not recognize as.
Right.
And also probably what it should definitely recognize as. So
yeah. I think if there is some very specific grammar rules that it should always follow when generating text, that I think will be an interesting thing to if we can actually verify that, that will be an interesting way to convince someone to use this network, for example. So in that sense, I think we can look at that, and also make sure that certain grammatical errors are never committed and so on. So yeah, I'll upload the code and
yeah, but certainly the other two properties are not. I mean, that should be will not have this kind of ambiguity. Specification
the properties are, in terms of properties, they're very specific.
Yeah. So as running and then understanding the system is one task. The other thing is specifying the property itself as and I think maybe you guys can come up with to discussion some document about some semi-formal way of specifying these properties as the first step towards encoding them in actual logic. Okay, yeah. So let's move on, Madhukar.
Yeah, certainly. Yeah, can you see my screen?
Yes.
Okay.
Maybe you could say where some of these folks are, just for historical interest. Gaikas is in somewhere in Israel, or where is it?
Yeah, I myself may not know all this, but yeah. So Gaikas is certainly
some of them. For example, Clark Barrett, he's the author of one of well-known SMT solvers and open source SMT solvers. He used to be at New York University, and right now he's at Stanford.
Okay.
And the SMT solver that he is credited for architecting is called CBC4.
Yeah.
David Gill is also a professor at Stanford, probably on long-term leave or something, but I don't know if he's back. He's certainly right now very active in Facebook. He is either leading or is part of a group that does apply these kinds of formal verification techniques for verifying, among other things, blockchain infrastructure verification. There's a group that was something that he was doing the last time that I interacted with him. The other person I don't know.
Okay. Yeah.
And the other two people I don't know.
Yeah. So do you know what kind of blockchain verification they are doing? I mean, I'm just interested. Is there any publication or something that you have come across? Or?
Not by David Dill. So there have been other, things that people have done. Okay. They mainly do verify smart contracts. Okay.
Okay.
Smart contracts is one class of verification. So smart contracts are these application layer on top of this infrastructure. Okay. The smart contract is actually a program that uses certain primitives as queries to these distributed. The infrastructure is like a distributed system, assuming that the distributed system satisfies certain properties. Okay.
Okay.
And on which these agents run. It verifies that when an agent submits a transaction, certain things will be guaranteed. Okay, that it runs out. That it does not. For doing that, it does not run out of certain gas.
Okay.
Or that it does not get in. So that is one kind of thing. And then there are things like, but I think the more interesting thing is verifying the infrastructure itself.
Okay.
That there can be some agents that are malicious, and they can do certain things so that maliciously they can make others, other agents, in such a way that it can make other agents don't get their due share of resources.
Okay. Yeah.
And that is, those things are more complicated because they need to, so yeah, I mean, yeah, so there are these kind of security issues with respect to that, that they are, I mean, that they withstand certain kinds of malicious attack.
Okay. Yeah.
In the context of a distributed system. So this is distributed system.
Yeah.
Verification. Okay, and I know that problem because Srinidhi Nagendra, one of a student, a PhD student at CMI, is working on that problem. He did do first for his master's thesis a smart contract verification of that Libra system that David Dill and Shaz Kadir are based on their semantics. But he's right now working on actually verifying the infrastructure. So these are the two kinds of things that people do generally, and David Dill and some of his colleagues at Facebook, they are interested in doing as well.
Yeah.
Actually, Subodh Sharma.
Yeah, he was interested in. Yeah.
He had with some folks at IBM. Okay.
Yeah. He had worked on something.
Yeah,
Zeus
that was once again for verifying smart contracts.
True. Zeus or something it's called, I think.
Yeah, they have built some kind of model checker or something like that.
True.
Bounded model checker, yes.
True. Yeah. So I think in the paper, at least it says that, at least this is a CAV 2017 paper where all of them, when all of them were at Stanford. So, yeah, so Clark and Clark Barrett and David Hill, certainly, as you said. And I think the other two were also maybe the PhD students or postdoctoral fellows. And Guy Katz, who is the first author in this one, he's currently at Israel. He's currently in Israel at, I think he's in Tel Aviv. Yeah. Okay. Yeah. So this one is So we have not discussed this algorithm. I mean, we have talked about it, but we have not described what it is. We know that it is based on the simplex method to solve.
Harsh had a question. Libra shut down. Okay. So anyway, sorry. It's okay. I don't know. What do you mean, Harsh, that it is shut down?
I remember like some news articles that regulators were worried that Facebook might be starting their own cryptocurrency, so they kind of did it under wraps or something like that. Like long time back.
But I know that Facebook never publicly announced it. Okay.
Okay.
But whether when you say it is shut down in the sense even the work on Libra is shut down at Facebook, that I don't know. Okay. If that project itself is scrapped, it had never reached a stage of acceptance as Bitcoin or something else.
Like it wasn't even decentralized, so yeah. I mean, it was somewhat centralized or something. I remember, but I need to check the news. Like I don't remember exactly what happened, but. Okay. Something like that, they had some falling out.
Could be. I don't know. I mean, I haven't checked the latest thing.
Yeah. So anyway, sorry. Yeah. So Guy Katz is at the Hebrew University of Jerusalem, is not at Tel Aviv. I'm sorry. Yeah. So the others, of course, are at Stanford, and Guy Katz in particular has done a lot of work in the last few years. He's done a lot of work in formally verifying these deep learning systems, which in this case, today we'll be talking about a feed-forward neural network. But I think, last time we saw a recurrent neural network. And quite recently, he has done some work on CNN's convolutional neural networks. And even some work, I think, I looked at some work where he had tried to do some bounded model checking to verify systems that are based on deep reinforcement learning. So you're training a system by doing reinforcement learning, the output of which is a policy which can be thought of as a feed forward neural network, and then you can try to verify properties up to a bounded length. So in fact, so there's a lot of interesting work, and a lot of it is fairly easily accessible to, given the kind of background that we have. And certainly after this course ends, the kind of background that you will all have, a lot of this research will be accessible, and this is an area which is gaining a lot of interest. So this is something that, if you are interested, you can certainly visit his webpage and homepage and know more about it. He's an assistant professor in the Hebrew University of Jerusalem. Yeah. Okay. So so we have spoken about simplex, and Sir had described how this works, and of course there are issues related to termination. One needs to of course the algorithm terminates, it's just that you need to convince yourself that it will. And we are not so currently we're not worried about these issues. We're just going to look at how simplex can be adapted to work for feed forward neural networks. And before this, I think I'm reusing some of the slides that I had used the last time, when maybe so some of this motivation may not be very necessary, but we do know that deep neural networks are everywhere, and they are artifacts, of course, produced by machine learning. And the way we get them is that we try to generalize a set of examples into a deep neural network. And the hope behind this generalization is that they'll behave correctly on inputs that have not been seen previously. Okay, and they're being used everywhere. I don't need to motivate this. And so this is again something that I think we have talked about. I'm not sure if we have looked at the details of this or not, but so this is a popular benchmark in feed forward neural networks, where they talk about an airborne collisions avoidance system. So it's about a set of directives that can be given to an own ship here, which you can see on the left. If there is an intruder aircraft coming from any of the directions, depending on some values of the sensors, like the velocity of the own ship, the velocity at which the intruder is coming, the distance, the angles, and so on. Okay, and the advisory that has to be given is whether you should continue to move in the direction that you're moving, or whether you should move to the right or to the left, or should you just take a slight right or a slight left, which is what has been denoted here: the slight left, and clear of conflict, and right and slight right. Okay. And the reason why this has practical significance is because the way these directives were being given, there was a lookup table, and the lookup table had different values of these parameters, and depending on you take a look at the current set of parameters, see where it matches in the lookup table. I mean, that's how lookup tables work. And then you would give the advisory that should be given for that one, except that there was a need to formally verify this thing. And the motivation of using DNNs was that the chip which had to be verified was not, it was difficult to put in a large lookup table of such a huge size. So this whole thing was replaced by DNS. Of course, it also makes it convenient in the sense that, of course, they're continuous in nature. So even if there is something which is not matching an exact row, you can, the DNN will still give you some advisory. But of course, when you replace such a lookup table by a DNN, the lookup table is, of course, easier to understand and to argue that it's not doing anything undesirable, because you can verify the lookup table entry by entry. And for each entry, you know that if it's not doing anything undesirable, you know that the lookup table entirely is not going to do anything undesirable. But when you convert that into a deep neural network, you don't know whether it will end up doing something undesirable or not. So therefore, there is a need to formally verify, and this was the motivation behind this work. This work appeared at CAV 2017. CAV is a reputed conference in the field of formal verification. Is a very reputed conference, and 2017 is when this had appeared.
Like, can't you just check, run the DNN on the lookup table and check if it matches?
Correct. Yeah, so you can run the DNN on the lookup table and it'll match. But now the DNN is going to even decide about inputs that are not in the lookup table. Right? Once you have
Like,
built
we
a
could
DNN,
just exclude those results, I guess.
no, because the whole thing is automated, and you need. How will you exclude certain results? So there are some
Okay,
sensor
you will
parameters.
need the lookup table to exclude the results.
Correct, and you will need the lookup table to exclude the results. So
Yeah. Okay.
yeah. So yeah, so once you have made it, once you have replaced it by a DNN, you will get some sensor inputs. It will certainly give an advisory for that input, and now you will not know whether it's right or wrong. So therefore, there is a need to verify them. Okay, so by formal verification of these things, we mean that we have certain properties in mind, and we would like to check that these properties would hold for all inputs. For example, if the intruder is far away, then the advisory should always be that this is clear of conflict. And if the intruder, let's say, is nearby on the left, then the advisory is always strong right. And of course, I've not formally defined these things. What do you mean by nearby? How close should it be? And and why should it be a strong right? And so these things. So of course, we'll give a formal. I mean, at least they in the paper they have given a formal definition of all these things, and the properties that are being verified have been stated formally, and then they have proposed that this can be done using the Reluplex thing that we are going to see today. Okay. Now, of course, how do these networks look like? So you have deep neural networks where these are fully connected. So you have these hidden layers where you have all the hidden neurons. We are assuming that the activation function on these is ReLU, which is max of 0, x. So this is the activation function, and so these are the inputs. These are the outputs, and then everything else is I mean, it's all a fully connected network. Okay. And of course, we know that these edges will have some weights, and then the layers will have some biases, and so on. Okay, so this is the general setup that we are aware of. I think we had seen this toy example, and I'll once again I'll show you how this can be verified. But I think we had seen this. So this for example is a very simple network. There is exactly one hidden layer with 2 hidden neurons, and the edge weights, of course, are 1. The biases are we have removed the biases. The biases don't add to the expressive power of a neural network. What you can do with biases, you can do without biases also. So it's not so the biases don't add to the expressiveness in any way. Okay, so we'll I mean, for most of our discussion, not just in this paper, I think in maybe a few other papers also, we'll not worry about the biases in each layer. Okay. So you have an input, you have an output, you have these connections, and there are certain properties that now you can specify and verify. And I think Diganta had shown this in the class. So there are 3 things. I think I have those scripts here with me. Can you see my screen?
Yes.
Okay. Yeah. So I think, earlier when Diganta was explaining this thing, he had shown that there are properties that you can specify and verify. For instance, using Z3 solvers. So for instance, in this network, you can ask this property that is it true that the input is always equal to the output, and it's possible to encode this. You can specify this constraint in the language of any constraint solver, we had used Z3 and the language of Z3. And so we declare these real values.
And clear deals when you book on clear. Book your next holiday now.
Hello.
Sorry.
Okay, yeah, sorry. Okay, so yeah, so what I was saying is that it's possible to, so if you have such a property in mind, it's certainly possible to specify this property in the language of a constraint solver. So you give the, so basically you take your network and you take the property and you encode this in the language of any constraint solver. And then you can ask if there is a solution to this. So for instance, this is something that you would have seen. So we have defined 4 real variables here, which are the values of these neurons. And then we have equations that say how, for instance, how can the value at the neuron 21, which is this one, how the value here can be computed based on this value and these edges and this edge. Okay. So this is, we are saying that, this is V11 times 1 because the edge is 1, the weight on the edge is 1. And then if this is greater than 0, then you keep it. If it is not greater than 0, then you make it 0. So this is an if then else expression, which you already know of. And yeah, so now so this encodes the computation as well as the ReLU activation.
Yeah, one thing that I might want to add is the ITE. So this whole thing, once you expand ITE, this whole thing will be in the logic of general propositional logic, with the atomic thing being drawn from linear arithmetic. Okay, so that's linear arithmetic plus. So once you expand, here Madhukar is showing it in terms of IT. I just wanted to relate it to the DPLLT plus Gen simplex that we have already seen. Okay, if you had DPLLT plus general simplex, the general simplex decision procedure that I covered in class is able to handle only conjunction of linear inequalities. Okay, conjunction of linear inequalities over the reals. That's what we saw. There are extensions to integers, which we haven't seen yet. Okay, maybe we will see it later on. But what ITE, when you expand it out, it adds the propositional layer. So gen simplex itself will not suffice. And we saw how DPLLT plus with theory solver of gen simplex could do this. And that's what is being done here. So I just wanted to relate that to what has been covered so far.
Yeah, certainly. And that's a very important point, because you see, this is the problem. The problem is that you don't know whether this value is going to be. So what is this? It says that, it essentially says that if this value, which is minus 1.0 into V11, if this value is greater than 0, then you retain the value, else reset. Okay, so this is what is being done, and in fact, this is the reason. This is what adds to the. This is why simplex is not directly applicable. You cannot have branching of this form, and this is the problem. This is why you need a specialized solver, which is what we are going to.
No. See, that's you're right. Okay, but what I'm saying is DPLLT plus gen simplex will work. Okay, and that's
correct. Yeah. True. I'm just saying that, so that's why simplex will not work. And of course, there are other techniques which work, certainly.
Yeah, what you're motivating towards, to make the point is, if you could bring the DPLLT into simplex itself to exploit, to make it a special purpose thing, in a more efficient thing than what the DPLLT, the online DPLLT plus simplex that we saw. Yeah.
Correct. Yeah. And I also want to highlight that this is the problematic part of the
Correct.
of this whole exercise. The fact that you don't know whether it's going to be retained or reset is the problematic part of this exercise. Okay. And then similarly, you compute the value of 22, you compute the value of V31, and then you assert that they are not the same. And you check if it is satisfiable. If it is satisfiable, then you know that it can be the case that they are not the same. Otherwise, you know that they'll always be the same, which is what the property says. Will the input always equal to the output? Okay, and once you have encoded this, okay, once you have encoded this, you can check this very easily using Z3. Sorry. Okay, and it'll tell you that this is satisfiable. So in fact, it is possible that the input and the outputs are not the same. And okay, and if you want to look at one such input, here is one such input for which the input and the output are not the same. Okay. Okay, so this model is returned by the solver. So here it says that if you start with an input of -1, you will get an output of +1, and therefore it's certainly possible that the input and the output are not the same. Okay. Okay. So the point that I'm trying to make is that given a network and given a property, there are ways in which you can verify this. Of course, the way that we have seen, it had a problematic part, which was the if then else, the existence of such if then else expressions, which lead to intuitively you can imagine that it will lead to a lot of branching. The more if then else expressions you have, the more branches will be there. If you have to decide whether something is satisfiable or not. And this is the problematic part of this exercise. Okay. Okay, so where is this motivation coming from to use simplex? So the motivation comes because linear programs are easier to solve, and piecewise linear constraints are reducible to LPs. Okay, and ReLU is a piecewise linear. This activation function is piecewise linear. And therefore, we will try to use simplex as a technique to do this. Okay. So the algorithm essentially is about it's a backtracking algorithm. So how does a backtracking algorithm work? So backtracking algorithms, like how you would know how SAT solvers work, right? So you have to decide whether something is satisfiable or not. So you try to take a decision or to make a decision about some variable having some value. And then you see if it leads you to a satisfiable solution. If it does not lead you to a satisfiable solution, you come back and you try to change the value that you had assigned. Okay. So this is what a backtracking algo looks like. I mean, any backtracking algo can be, it can be thought of as a SAT solving algo. SAT solvers, the way SAT solvers work. This is typical of any backtracking algorithm. Okay. So you want to fix, you don't know whether, as I said, you don't know whether the value at any neuron will be retained or will be reset by the activation function, depending on whether it's positive or not. So, and I mean, you call this the active and the inactive state, the fact that, it's retained or reset. So they say that the general idea that they have proposed is that you don't worry about whether it's going to be, I mean, the backtracking algo says that you don't worry about whether it's going to be this or this. You fix it to be either active or inactive, and then you can try this and you can solve the resulting linear program. If you get a solution, then it's great. If you don't get a solution, you go back and say that, oh, maybe I fixed this as active. Let me try to go back and change this to inactive. Okay, so this is a very simple backtracking algorithm that can work to decide whether a property holds for a given neural network or not, when you have ReLU as activation function. But this is not very interesting because you'll have to backtrack too many times. There are too many neurons. So typically, even in these ACAS benchmarks, there are close to 50 hidden layers. I think there are close to 50 hidden layers or no, maybe 6 hidden layers with 50 neurons each. So basically there are 300 hidden neurons with ReLU activation function, and you have to decide about each one being active or inactive. And therefore, you have to take too many decisions. Many of them will go wrong, and then you'll have to backtrack. Okay. So therefore, this backtracking algorithm is not an interesting thing to do. Okay. Of course, this is, because there are 2 decisions at each neuron, this is exponential in the number of ReLU nodes. Okay. So this is the motivation part of it. If you have any questions, I think this will be a good point to, or if you have any comments or remarks, this will be a good point to stop in. Okay. I hope I'm connected.
Yeah, you are. Okay, so that is fine. So I guess you guys, listen to the thing. And one of the things that I will, ask you to, once Madhukar presents this, okay, so the third bullet is the important thing. So it extends the simplex method to do with ReLU. Okay, everything that he's talking about today can be done using an SMT solver, which in turn means that DPLLT plus general simplex. But certainly this is a lot more efficient, okay? And there is a comparison also. So I will later, in one of the things I want you to do as a follow-up is to compare this extension, this ReluPlex, and the way it works with the DPLLT plus simplex. So pay attention. Okay, and I want you to contrast the 2 things. Yeah, that's all I want.
Yeah. Okay. Yeah. So as sir is saying, so this, we know that this as in we have talked about this, that this extends the simplex method, and we know that one way to do this, one way to solve this problem is to backtrack. So for every ReLU, you decide whether it's going to be active or inactive. And then if you're not getting a satisfiable solution, you go back and change your...
Which is exactly what SAT solvers do, the DPLLT plus simplex.
Yeah, which is exactly what...
Sometimes might work if the heuristics works. If not, it may not, you may end up in this the worst case scenario. And and what would be interesting to see is how does ReluPlex improve upon that. Yeah.
True. Yeah, certainly. So that's what I was saying. So this is the backtracking algorithm which SAT solvers and SMT solvers implement. In fact, they have, over a period of time, they have made this backtracking so efficient that many times it works in practice, but in the worst case, of course, it is exponential. Okay, and we will try to look at one method in which we cannot do this backtracking. It cannot be avoided in general, but we are trying to see if it's possible to delay it. Okay, so therefore the way ReluPlex works is that it does not require case splitting in advance. So we don't split immediately on whether something is going to be active or inactive. We try to ignore certain constraints and then do the splitting only if it's really necessary. And some of these things will become clearer as we move along. So let's look at one such property which we'll try to understand. And I think this is again one property which Diganta had explained. I have the code, so I'll go through it again. But this is something that you've seen. So this is the same network that we just saw a couple of minutes back. But we are now asking for a different property. Earlier, the property that we had asked was whether the output will always be equal to the input or not. And we saw that it need not always be equal to the input. In fact, if you take -1 as the input, the output will be +1. Okay. So here we are asking a different question. We are asking whether it is possible that the input is between 0 and 1 and the output is between 0.5 and 1. Is this possible at all? So let's first see whether it is possible or not. So I have a similar encoding. I've encoded this as prop3 earlier. This is the same code as Diganta had. Okay, and this is the property. Is it possible for the input V11 to be in 0,1 and the output to be in 0.5, 1? And the encoding is exactly the same. I will not go through the encoding, but let's just see whether it's possible to do it or not. Okay, and it turns out that it's possible to have the input between 0 and 1 such that the output is between half and 1. And what is such an input? This input is 1 by 2. Okay, so if you have half as the input, you will get half as the output, and therefore it satisfies your constraint that it's possible to have this as half such that this is also half. Okay, now let's try to see. I mean, of course, this we solved using Z3, but let's try to see whether we can do this using the technique that these guys have proposed. Okay, so how does this technique work? So they say that, so you have this this network. This is the input layer, this is the output layer, and this is the hidden layer where these neurons have a ReLU activation function. So they say that if you take any neuron that has the ReLU activation function and split it into two neurons, I mean, think of them as two neurons. Okay, there is a backward facing neuron which is towards the previous layer, and there's a forward facing neuron which is towards the next layer, and they are connected by a ReLU connection, let's say. Okay, so the way to understand this is that you do the so remember that, you know, how does this computation work at a ReLU node? So there is a weighted sum that is being computed, and then you apply the activation function on that. Okay, so here we are trying to separate these parts. So the backward thing will compute the weighted sum, and the activation function will be applied by the forward facing neuron. So this is applied by the ReLU connection, and therefore the forward facing neuron will have the final value, whether it is reset or whether it is retained. Okay, so you imagine that the every neuron as this backward facing neuron and a forward facing neuron, and between the forward and backward facing neurons, of course, they are connected by the activation function. So between V21B and V21F, the relation is very simple. V21F is equal to V21B if V21B is greater than equal to 0, else V21F is equal to 0. Okay, so this is the activation function part of this process. The rest is very simple. So how is V21B calculated? So V21B is V11 into 1. Okay, so this is what you do for every ReLU node, and we assume that there are only ReLU nodes and the ReLU is the only activation function. Okay, so you have these backward variables, and then you have these forward variables, and you separate the task of computing the weighted sum from the task of applying the activation function. Okay, so this is just the same network is just a way of imagining how things are happening. And for every variable, you have now these two variables that you have introduced, a backward facing thing and a forward facing thing. Okay, so now let's try to encode the network. Of course, you know, for simplex also the constraints have to be presented to the simplex solver in a certain way. Similarly, for reluplex also the constraints have to be presented in a certain way. So let's try to encode the network that we have. So we have VB21 is V11 into 1. Okay, so instead of saying that VB21 is same as V11, we will say that VB21 minus V11 is A1, and then we will force A1 to be 0. Okay, similarly, what is VB22? VB22 is minus V11, so VB22 is equal to minus V11. So we'll take this on the other side. We'll say that VB22 plus V11 is equal to 0, And instead of this, we'll call it A2 and we'll force that A2 is 0. Okay. So A2, which is V11 plus VB22, this is the equation, and we'll force that A2 is equal to 0. Okay.
Yeah, in terms of what, yeah, this is actually the tableau. Okay, so these are the additional variables, what I call as additional variables.
Correct. Yeah. So they're called additional variables or slack variables in the literature. Yeah. Okay. Similarly here, so the forward facing ones can be related using this if then else expression. Remember that, I'm not relating them. I'm ignoring this constraint for now. Okay. So I'm not writing anything about, how VF and VB are being related for any 21, 22, 31, whatever. Okay. So I'm going to ignore these if then else constraints for now. Okay. So I've related VB21 with V11, VB22 with V11. Now I'll relate the 31 with the forward facing things. Between the backward and forward, I'm going to forget the relationship for now. Okay. So this is also very simple. So what is V31? V31.
So by ignoring for now, what I presume you mean is that, go to the next slide. So it means that VF21 can be anything, correct? Right now.
Correct. Yeah. So it is unconstrained. Yes, it can be anything.
Yes. Okay.
Yeah. Okay. So what is V31? V31 is V21 F into 1 plus V21 22 F into 1. So this is V21 forward plus V22 forward. Okay. So instead of writing as this equality, we will write it as this minus V21 forward minus plus this is equal to A3, and then A3 must be equal to 0. Okay, so I've encoded the network like this. Remember that there were two ReLU neurons, so therefore there are two ReLU pairs. The ReLU pairs are, there is a backward and forward of the neuron 21. Similarly, there is a backward and forward of neuron 22, and there is a constraint that relates these two, but I am not worried about this constraint right now, which essentially leaves, as Sir was saying, which essentially leaves these variables unrestricted. Okay, so now let's take a look at all these variables that we have. So we have V11, which is the input. Then we have backward and forward of 21. Then we have backward and forward of 22. Then we have 31, which is the output. And then we have these A1, A2, A3, which are the additional variables. Okay. Let's understand the lower bound. So remember that, what was the property? The property that we wanted to check was whether it's possible for V11 to be between 0 and 1, such that V31 is between half and 1. Okay, this is the property which explains the lower bound of V11 as 0 and the upper bound of V11 as 1, because this was to be between 0 and 1. Similarly, for 31, it has to be half and 1, which you can see here. Okay, these variables don't have much of a choice because there were these equalities which we have transformed into using these slack variables into these equalities. So all of these are forced to be zeros.
They're dependent variables.
Yeah. Okay. So they are their lower bound is 0 and their upper bound is 0, which explains these zeros here and the zeros here. Okay. The forward facing variables, remember that they cannot be negative. This is the ReLU activation function, right? So this is a ReLU activation function. So it has to be max of 0, x. Okay. So the max of 0, x can only be bigger than or equal to 0. Okay. So therefore, the forward facing things have a lower bound of 0 and there's no upper bound. Similarly, V22F has a lower bound of 0 and there's no upper bound. For V22 backward, there is no lower and upper bound. So therefore, this lies between minus infinity and infinity. Okay. So this explains this table that we have. Okay. we start with an initial assignment of 0 to everything, which is fine for A1, A2. In fact, it's fine for a lot of things. It's fine for V11. It's fine for all the backward and forward things. It's fine for A1, A2, A3, but it is not fine for V31, which is the output, because it had to be between half and 1. So you cannot have a value which is 0. 0 is not between half and 1. Okay. So this is a non-basic variable. So these are the basic variables to begin with. The variables on the left side of the equality are basic variables. Okay. So this is a non-basic variable. Its value is not within the bound. So you update it and set it to 0.5.
Yeah. So where does the basic and non-basic division happens here? A1, A2, A3 are the basic variables.
Yeah.
All the rest are non-basic.
All the rest are non-basic.
Non-basic. So yeah, I mean, even V31 is non-basic. No?
Yeah.
Okay, because it has bounds on them. Correct.
It has bounds. Okay.
Okay.
Okay. So how is it done? So and you have these equalities that that we have to begin with, right? Now V31 has to be increased by half. If V31 has to be increased by half, A3 will increase by half, because if you increase. So this is an equality. If you increase the right hand side by half, the left hand side increases by half. So you update, and so first of all you said you bring this in the bound. So V31 is brought in the bound by updating it to 0.5. Okay. Consequently, A3 becomes 0.5, but A3 A3 has bounds, so A3 cannot remain. A3 has to be 0, so it cannot remain half. So you pivot it with some variable, which is, I mean, you choose this because this is right now this is unconstrained. Okay, so you choose to pivot this with a V21 forward. So your equations now change. Of course, the first two equations don't change because you don't do anything here. So A1 continues to be minus V11 plus VB21. A2 continues to be V11 plus VB22. But now this thing changes. So your A3 comes here, your V21 forward comes here. Okay, and now the assignment is that V3 is half. Okay, this is 0, this is half. Okay, this is 0, and then everything else was 0 anyway to begin with, right? So you have this assignment. Okay, which means that all variables are within bounds, right? Because the problem was that this was out of bounds. So this was 0 and the bound was 0.5 to half. Now you have increased this to 0.5. And how you have increased it here? You have increased it here by adjusting this to 0.5. But it is fine to adjust this to 0.5 because the bounds are 0 and infinity. So therefore it's fine to adjust it here. Okay. So now as soon as you do this adjustment, everything is within the bounds, and therefore you have reached a solution. The only problem here is that this constraint that you had chosen to ignore, which is now it cannot be ignored anymore, because the solution that you have obtained here, where you have increased this to 0.5 and therefore you have increased this to 0.5. So the solution that you have obtained here is inconsistent for this network. Why is it inconsistent for the network? It is inconsistent for the network because look at the so look at this V21 forward. So V21 backward is 0, V21 forward is 0.5, and there is no way this is possible. So there is no way it's possible to have let me erase some of it here.
So this part, the first part, is violated.
Yeah. So there is no way it is possible for this to be 0 and this to be 0.5, because the only thing that connects these two is the ReLU activation function, which says that if it's 0, the only thing that you get here is 0.
The else part is violated.
Correct. Yeah, I mean, whichever way. Here I had said greater than equal.
Greater than or equal to 0.
Okay. Yeah. But the point is that it can never increase. What you get at forward, it can never be more than what you have obtained at no, yeah, sorry, it can be more than that. I'm saying that, on the positive side, it cannot be more. If V21 backward was negative, it will certainly be more. But yeah, essentially you get the idea, right? So therefore these are connected by some constraint. We had chosen to ignore this constraint. Therefore this if then else was not given to the simplex. And the reason why it was not given to the simplex is because you cannot give such constraints to simplex. This is a limitation of simplex. You cannot give it if then else constraints. Okay. So therefore this constraint was not given to simplex. We were simply hiding this constraint from the solver. Of course, when we are hiding such a constraint from the solver will think that V21 forward is unconstrained. If it's unconstrained, it's going to take its, it's going to do certain things that it thinks is allowed, but it is not allowed, which is what we mean by, this ReLU pair breaking. Okay. So what happens when a ReLU pair breaks? When a ReLU pair breaks, you try to fix the ReLU pair. Okay. So you fix it by setting V21 backward to also 0.5. Okay. Now the ReLU constraints are fine, but A1 is out of bounds. Why is A1 out of bounds? Because notice that, V21 backward has been set to 0.5. This is still 0. So therefore this is 0.5, and which is out of bounds because this has to be 0. Okay. So then you fix A1 with a pivot step with V11, and therefore you set
one moment, Jay. So fixed by an update step. So this update step is not there in the simplex. So that's what. So that's the additional step. Huh? So to enforce the constraint that was violated, the forward was not. So see, in simplex.
Correct.
Yeah. So because yes, so you are enforcing that V2BB, the back variable, should be 0.5 also, because they have to be equal, right?
Correct.
Yeah. Okay.
Yeah. So this fixing this the ReLU pair breaks, and this must be fixed before we can go to simplex again. So the way it is fixed by setting V21B to 0.5, because this is the only thing that can explain V21 forward as 0.5, and therefore this setting is done. And then of course the ReLU constraints are not a problem anymore, but A1 is a problem now, because A1 had to be 0. You have chosen this to be 0.5, so therefore you must choose this to be 0.5. So therefore this is minus 0.5 and this is plus 0.5. So therefore this will become 0, and therefore A1 will be 0. Okay. So therefore A1 is fixed by doing a pivoting with V11. Okay. And now the equations change. Okay. So your V11 comes on the left, A1 comes on the right. So now the basic variables are V11, A2, and V21 forward. Okay. Okay. So the non-zero assignments at this stage are what? So your V11 gets 0.5, V21 backward gets 0.5, because this was done to fix the ReLU. V21 forward was 0.5. The output was half, and A2 of course is half, but A2 is out of bounds now. Okay. So the moment you do is there a mistake? I'm sorry, just 1 second. Correct. Yeah. Okay. So this one you had said to. Okay. So yeah, I'm sorry. Some of this is difficult to bookkeep. But the point is that V21 was reset to 0.5, for which this had to be. This was increased to 0.5 because this was in the negative thing. So negative and positive will make this 0. But the moment you increase V11 to be half, remember that this was still 0, and you have made it half. So therefore A2 is now out of bounds. Okay. So this is the effect of what you have done. And once you have done this, A2 is out of bounds. So A2 is pivoted with VB22, because VB22 is unconstrained. So therefore, A2 is pivoted with VB22 and then it is set to 0. Okay.
Just one clarification. So I think in your table, what is basic and what is not basic is kind of not exactly. So after the previous step, what happened? Go to the previous slide. So I just wanted to understand this. So here the equations are B11, A2. This was not the original one. The original, okay. So what happened was, so now the dependent variables, you have pivoted.
So we pivoted A1 with V11.
So therefore V11 comes here.
Correct. So V11 comes here. So V11 has become basic.
Yeah. So
Everything.
that is not reflected in the table. That's what's no. But maybe you're not exactly showing in the table exactly which ones are basic after this pivot step.
Correct. Yeah.
So that is one thing that yeah. So when you move to the next table in the next slide, I just wanted to, so because you're still showing all of them in the same. So I guess these, yeah, but you're still showing A1 as 0, 0 thing. Yeah.
Correct. Because I'm doing both these pivoting in the same step. So V11 had to be increased to 0.5, which breaks A2. Because this is 0.5.
So which are the basic ones here?
So for me, the basic variables are always variables. So I'm maintaining 3 equations.
Correct. Yes.
These 3 equations, the basic variables are on the left-hand side of this.
Okay, so they are the ones which may potentially violate their constraints. All the non-basic ones satisfy their constraints. Okay, so after you switch, so you switched which one? V11, you brought V11 here and switched.
Yeah, so this is what.
You brought V11 here and yes.
Yeah.
Okay, so V11, A2 and V2F1. Okay.
Okay, so these are my non-basic, these are my basic variables now.
Okay, after your complicated, I mean, somewhat more involved pivot, because there's an update step also here. Okay.
Correct. Yeah. Okay. So now this is within the bound, this is within the bound, and this is not within the bound.
Correct. Okay. But all the other ones, V2FF, V31, and A3 and A1, they are all
they are all within the bound.
In the bounds. Okay.
Yeah, because A3 is 0, this is half.
Yeah, they are the basic now. They are the basic ones. So there's non-basic are 3. Yeah.
Yeah. Okay. So now, of course, A2 is now out of bound, which is the last thing which is out of bound now. So therefore, this is pivoted with VB22, because VB22 has not been constrained so far, and then it is set to 0. Okay, so you set A2 to 0, but in the order in order to set A2 to 0, you increase VB22 by half. Sorry, you decrease VB22 by half. Okay, so VB22 now becomes minus half. Okay, which is clear from here. Okay. Okay. So essentially, what is it that we have been trying to do here? We have been trying to fix the ReLU pair as and when one breaks, and then we come back and do how simplex would solve the remaining constraints. So we are trying to solve a bunch of constraints using the simplex method, but whenever we get a solution, we try to check whether the solution satisfies the ReLU constraints, which have not been specified. We have tried to hide it from the system, and they have been kept aside But whenever we get a solution from simplex, we quickly check if it satisfies all the ReLU constraint. Okay, and so this is the process. So you have your simplex method, which is doing all the solving, and then whenever you get a solution, you check whether all ReLU pairs are fine. Okay, this is a constraint which you have not specified in the simplex system, because it's not possible to specify this in the simplex system. It's an if then else expression which can be thought of as a disjunction, and it's not possible to specify a disjunctive constraint in the simplex system. So therefore you don't do this. And the way you try to mitigate this is by saying that, okay, I'll hide this disjunctive constraint from the system. Let me give it all the other constraints. Whenever it comes up with a solution, I'll check whether this already satisfies my disjunctive constraints or not. If it satisfies, then you obtain a solution. If it Devjit, you had gotten disconnected, is it?
Well, I don't know. Is he not? So you look at the participants list. Participants. No, Devjit is still here.
Yeah.
Everyone seemed to be there.
Okay. Yeah. No, it asked me to admit Devjit again, so I was wondering.
Could be. I mean, I don't know.
Yeah, sure. Sorry. Okay, so this is what we are trying to do. We are trying to use simplex. We cannot specify all the ReLU constraints in here because this is disjunctive in nature. Therefore, we keep this aside. We give all the other constraints to simplex, get a solution, and check whether it satisfies the ReLU constraints. If it does, then we are done. If it does not, then you fix the ReLU pair and then try to do simplex again. Okay, and this is something that they claim does much better than specifying all the constraints upfront. Because if you specify all the constraints upfront, then you'll have to decide whether a ReLU neuron is active or inactive. And then based on these decisions, if some of these decisions go wrong, you will have to backtrack and fix them. Okay, so this is the idea behind their algo. Now, one of the things that's important to understand is what happens if this goes on. So you solve your simplex, you get a solution, some ReLU pair breaks. Then you fix that ReLU pair, you go back, and once again you get a solution and some ReLU pair breaks. Okay, and this can go on and on. Okay, so the way they fix this is by saying that, you know, if the same ReLU pair keeps breaking, which means that, you know, if the same ReLU pair breaks more than some you know, t times, or I think the number that they used in the experiments was more than 10 times. So if the same ReLU pair breaks more than 10 times, then they don't hide that ReLU constraint from the solver anymore. Okay. So now what is it that you can do? You cannot give this constraint entirely because this is disjunctive in nature. You know, in the active case, the constraint looks like this. In the inactive constraint, the case looks like this. And you cannot give this or this to the solver. So therefore, you create two copies of your problem. For one copy, you give this particular constraint. For the other copy, you give this particular constraint. So one goes here, the other one goes here, and then you solve these two in parallel. If any of them give you a solution, then you're done. Okay. So now what is really happening? So if the same ReLU pair keeps breaking again and again, you are eventually going to do the case split anyway, right? And whenever you do a case split, you will create two copies of the problem. Okay. So in the worst case, if you go and do a split on every ReLU, this is again going to be exponential in the number of ReLU nodes. Okay. So in the worst case, of course, this can be as bad as any other backtracking algorithm. The claim that these guys make is that if you solve simplex and hide the ReLU constraint, then it is very often the case that the solution that you get from simplex satisfies these constraints already. So you don't really have to do, these things don't break more than, at least a large number of things, a large number of ReLU pairs do not break more than t times. Okay, which avoids the case split. Okay, so
how do they determine t? How long?
I think this is experimentally determined, but for this they have used 10 as the limit.
So you could kind of by experience or something pick that t. So if it doesn't terminate and keeps doing the same thing, then you split. Huh?
True. Yeah. So if the same thing breaks again and again, or so yeah. So I think this has been experimentally determined, but the point is that it doesn't happen with too many neurons that they break more than 10 times. This is the idea that they have used. So in terms of the algorithm, it's not very different. It's not fundamentally different from a backtracking algorithm or something that decides on a case by case basis. The only thing which makes it very efficient is the fact that you delay the case split as far as possible, and very often you don't even have to do the case split. Okay, so this is a heuristic, so therefore it's a heuristic. The algorithm in the worst case remains as bad, but this is a very efficient heuristic. This has been a very popular piece of work, and I think that it's widely cited and used.
So this itself can run under, instead of DPLLT plus gen simplex, in which all the case split is done at the higher level. Instead, you could still use DPLLT and then use this ReluPlex, which will somehow, try to see without case splits if it can get it. If not, it'll throw up, and then say, oh, well, I could not, okay? And then you can case split, right? So, which is what is happening.
Correct, yeah. So in fact, this is a technique that's also used a lot of, at several other places also. So if you have a large bunch of constraints, sometimes it helps to decide on a subset of these constraints at once, and then check some of the other constraints which may not be, which may not have such a big impact, in the sense that, there are, so what is happening? So this is basically, a big bunch of things from which you try to hide, all these ReLU constraints on this side. And you say that, okay, let me find a solution for this one. And every time I find a solution for this one, I'll check in these constraints whether this is being solved already or not. So as a technique, I think this is used at a lot of other places also, especially when you're trying to optimize certain tasks or something. So to solve the entire optimization problem may be very difficult. So you may solve a part of the optimization problem and see whether it's good enough or it's close to the optimal with respect to some of the other constraints that you may have hidden. So this is a side remark, but the only thing that I'm trying to say is that, as a technique, this is also applicable in certain other applications and domains. Okay. Okay, yeah. So very quickly, I'll wind up in the next 2-3 minutes. So one of the few things that make this, there are certain other tricks that make this efficient. One of them is tightening of bounds. So basically, you have certain equalities and inequalities. And if from these equalities and inequalities, if you can find a tighter bound for some of the variables, then it can help you reduce a case split. For instance, in this case, x is y plus z. And let's say, if you have these constraints, this is the equality that you have been given, x is equal to y plus z. And these are some inequalities that you have, that x has to be greater than or equal to -2, y has to be bigger than or equal to 1, and z has to be bigger than or equal to 1. So now once you know that y and z have to be bigger than or equal to 1, you know that x has to be bigger than or equal to 2. So therefore, you know that, even though this is the constraint that has been given to you, you can find a much tighter constraint, namely this. And if you can find this constraint, then you don't have to worry about, something being less than 0 and therefore being reset or something. Okay. So such tricks can help you get tighter bounds and reduce case splits. Okay. One other thing that helps them is to use floating point arithmetic, because a lot of these edge weights and after all the computation that happens, you get a lot of floating point numbers. So if you use precise computation, it can be expensive. So you can use floating point arithmetic, and you can round off. You can keep the errors rounded off to a very small amount, and these are some things that can help them achieve scalability in practice. Okay. So they tried to experiment with these things, and the properties that they looked at was that there was no unnecessary turning advisories. When the ship was not supposed to turn, you don't advise it to turn. And then also, some interesting things that you can observe, that the alerting regions are consistent and symmetric. So for instance, in this region, if you are telling the own ship to turn slightly right, then there is a symmetric region in which you are telling it to turn slightly left. Similarly, there is a weak right, there's a symmetric region which is weak left. Okay, so these regions are symmetric. There is some symmetry in this thing. Okay, it's important to maybe some of this will become more relevant later when Diganta will talk about some of his work on exploiting such symmetry in deep neural networks, or finding out such symmetry in deep neural networks. But it's clear that this has a very symmetric nature. If there is an intruder aircraft coming from the left, then you would do certain advisory. Now, if there is a mirror image of that situation, if the intruder aircraft is coming from the right, then you will do a mirror image of the advisory. So in some sense, there is some symmetry here.
So this network satisfies that symmetry property?
So it does that.
No. But in all cases, does it? Because
so it's not clear that in all cases. In fact, you can see from this thing that it's not exactly a mirror image, but I think it's very close to being a mirror image. These regions which are strong and weak to the right and strong and weak to the left.
So there is some tolerance where up to which this symmetry holds good. And
correct. But if you see this, these are actually, if you see this as the line, then the weak right thing here is symmetric to the weak left thing here, and the strong right thing here is symmetric to the strong left thing here.
But I see a little bit of blue going into it and things.
Correct. So there is a little bit of this thing
and
here.
Then there is a bit of a green here. You see?
Correct.
There's a bit of a green here and a bit. Oh, that's your thing. Oh.
Yeah. Sorry. So this is the original.
Even without your thing, there is a blotch here and there's a blotch here. You see, there's a blue blotch here and the green blotch here.
This one.
Yeah.
Correct. But once again, these are symmetric, right? I mean, this is.
But the shape of this is different than that. So
correct. So I'm saying that, it's not exactly, maybe, it's not mathematically, you cannot say that this is this, but under some tolerance, I believe that you can still argue that they are symmetric.
Maybe we should revisit this later on.
Yeah.
Get to cover Diganta's thing in here so that they can do it. Yeah. Go ahead, please.
Yeah. So I think it's 5 o'clock, so I should stop now.
I think we should stop here because they all have to go. So I will, in the next, So,
in the next class, I'll cover there are some 2 or 3 points that are remaining. So I'll cover this, and then I'll talk about an abstraction refinement technique to make this process more.
That you can do. Yeah. I think in the next class, even if you don't want to get into the thing, so I want to contrast the simplex and the other one. Okay. I mean, I'll give as a follow-up exercise for them so that they will read this paper as well as the way the Gen simplex, paper a little bit, and then they'll contrast that. Okay. So that will make them understand a little bit more deeply. Yeah. Okay. So good. Yeah. Okay.
Yeah, so I've uploaded the paper and the slides in Moodle already, so you can take a look at that.
I've also uploaded the Gen simplex paper. Okay, so you will certainly need to read those 2 papers in one of the follow-up exercises that I had planned to assign to you as a presentation assignment. Yeah.
Okay, sir.
Yeah. If you have any questions, we can begin the next class with those questions.
Surely, yes. Yeah. Okay, I'm going to stop recording.